So this is the third part of the nuclear chemistry series in my YouTube videos, and in today's talk we're really going to focus on fission and fusion. We're going to start by comparing and kind of contrasting radioactivity to fission and fusion only in so much as we look at the energy and the general overall reaction. Then we're going to talk about what's called mass effect and give its implications for creating energy in a nuclear reaction. We're going to look at Einstein's famous equation, which explains how in a nuclear reaction so much energy is created. We're going to be familiar with the binding energy curves, know how to draw conclusions about the tendency of a nuclide to either undergo fusion or fission. You can use these to make predictions about which way the reaction will go. Know how a chain reaction works, how it's controlled in a nuclear reactor or in a nuclear powered engine, and know how fission and fusion are utilized and where they're seen in nature. Be familiar with the pros and cons of each. Going back to this earlier slide where we were comparing nuclear reactions to normal chemical reactions, and we're using coal burning as our kind of baseline example, where if you burned a gram of coal you create about 90 kilojoules of energy. In comparison, just radioactive decay, normal radioactive decay, has a very similar order of magnitude to the energy it creates. And in this example, remember, it's a very an unstable nucleus will emit particles till it becomes stable. That activity always emits energy. Today's focus is going to be more on fission and fusion. So fission occurs when a very large unstable particle is disrupted by a neutron propelled into its nucleus, and it will actually split into two smaller nuclides, which tend to be on their way to becoming more stable, although they usually undergo additional radioactive decay. But in the process it releases 3 additional neutrons, and that's a very, very important component of fission. Now we've increased the kilojoules per gram by an order of a billion, 10 to the 9th. And then finally, fusion is where 2 very small nuclides collide, 2 small isotopes collide, and they make a larger isotope. And usually in the process, as you saw in the demonstration, it releases another neutron. And again, orders of magnitude are 10 to the 9th kilojoules per gram. But comparing fission to fusion, it's about 3 to 4 times greater. So what gives rise to all this energy? It's something we call mass effect, and it's in essence saying that in this kind of chemical reaction there's usually a little loss of mass, and that mass is converted into pure energy. And this sort of reaction, if you talked about it a few generations ago, people would have said that there's no such a thing because matter is always conserved in chemical change. But now we have to modify that to say matter is always conserved, except in the case of a nuclear reaction where matter is turned into pure energy. So here's if you study this reaction, you look on the reactant side, you have a large particle, unstable particle. It interacts with a neutron and it splits into 2 smaller isotopes which are approaching becoming stable, but these both are radioactive as is, and releases 3 neutrons. So this is the fission reaction. So let's just see what we mean by this mass effect. If we very carefully measured the masses of all these particles that we have in the reaction and summed up the reactants, you'd have 236.05258 AMUs. If you summed up the products, you'd have 235.86769 AMUs. And that is a small loss of mass of about 2/10 of an AMU. If you convert that to kilograms, and I'm doing this just so I can kind of get to an energy unit, and then you apply Einstein's famous equation, which just says if you know how much mass is lost in a chemical reaction, you can multiply it by the speed of light squared, and you'll be able to calculate the energy created in a nuclear reaction. And for this calculation, instead of using the simplified 3 times 10 to the 8th meters per second, we need to put in a lot more uncertainty so that our calculations are very precise. So you square the speed of light multiply it by the mass in kilograms, you actually have around 2.8 times 10 to the minus 11th kilograms. You end up with 2.8 times 10 to the minus 11th kilograms meters squared per second squared. So now you know the amount of joules per every U-235 atom that undergoes fission. If you want to put that to compare to numbers you're probably more familiar with, you'd need to think about a mole of uranium-235 undergoing fission. Use Avogadro's number to do the conversion. Again, you need to put in a lot more precision. Make the conversion to joules to kilojoules, and you end up with this number that we had talked about earlier on the order of magnitude of 10 to the 9th kilojoules for every mole of uranium-235 that undergoes fission. Now, a lot of times in nuclear chemistry, instead of using kilojoules and joules, which are helpful sometimes because we want to compare it back to our regular chemical equations, we use what's called the electron volt. And the electron volt is the kinetic energy of an electron that has been accelerated through a potential difference of 1 volt. And to further understand that, you might want to look back to the electrochemistry sections where I discuss voltage and what it means. We're going to kind of look at this idea that there's about 1.6 times 10 to the minus 13th joules in every mega electron volts, or million electron volt. And then another term that we use a lot in this little section of radiochemistry is what's called the nucleon, because when it comes to mass and mass loss, we look at the fundamental particles of the atom that are pertinent to mass, and that would be the proton and the neutron. And these have their own name. We call them nucleons in particular. So how do you measure these small isotopic masses? I'm just going to jump off for a minute and just look at this, just because you're going to see a lot of these numbers and they're very precise, maybe to tens of thousandth or hundreds of thousandth of a gram. So at that point you're probably wondering, well, how do you measure that? There's an instrument called the mass spectrophotometer, or the mass spectrometer in this case. This one in particular is called an isotopic ratio mass spectrometer, but most mass spectrometers work on the same principle. In this diagram that I had borrowed from a paper by Muscio and Jackson in mass spectrometry, we're measuring the mass of different isotopes of carbon dioxide. The carbon dioxide might have different masses due to having either carbon-12 or carbon-14 or carbon-6 or oxygen-16 or oxygen-18 present. So what you do is you bring the carbon dioxide into a chamber with inert gas helium. You under extremely high voltage, you charge up the particles, you accelerate them into this magnetic field that basically starts to curve them based on their charge being affected by the mass. And the higher mass has a more momentum, so it doesn't curve as much. And then the lower mass gets curved more. Remember that second law. The amount of acceleration or change in direction is based on the mass and the force. So we have a constant force acting on this mass. The more massive one curves less, the less massive one curves more. And then you have a detector that basically analyzes, in this very simplified diagram, their position of where the particles come through correlates with whether it's the carbon dioxide 46 or the carbon dioxide 45 or 44. And that's just the general idea. I like this diagram, very simple. Here's some real data on silicon analysis, where we're looking at the different isotopes of silicon, and you can see by the peak height. So here's a mass spectrometer analysis of silicon, and you can see by the peak height that there's more percentage of this silicon 28 than there is of the silicon 29, and so therefore it has a higher peak height. You integrate the area under the peak, and it correlates directly with the amount. But again, the point being, this particular instrument measures the very, very precise, gives you a lot of significant figures in the mass. So that's how we come up with these numbers, because we're going to be using them throughout this talk. So let's just do a little calculation. This would be good to get you moving. Why don't you find the mega electron volts associated with the loss of just one atomic mass unit? Remember to use Einstein's equation And then I'm going to go ahead and remind you what this conversion is, that there's 1.602 times 10 to the minus 13th joules in every mega electron volts. So at this point, what I'd like you to do is stop the video, try your calculation, use your dimensional analysis. When you are done and you're comfortable with your answer, you can restart the video and check your work. So let's see how you did when you basically set up the equation. In this case, it's the amount of kilograms per 1 AMU. Multiply it by the speed of light squared. Plug and chug. Do your last, use your conversion here in this next step, and solve that there's 931.5 mega electron volts in every 1 AMU. And this is a good conversion factor to know when you're doing this section of nuclear chemistry. So let's look at the mass loss associated with fusion. Again, we're assuming that you have been given the data, it's been analyzed by mass spectrometry. Otherwise, there's no way you would necessarily know that. But the constants for the two fundamental nucleons, the proton has a mass of 1.00783 AMUs. The neutron has a mass of 1.00866 AMUs. And as you've learned in probably chemistry 1, you always assume those are about 1, and that you can see that that's true. But when you get more significant figures, the neutron weighs a little bit more, and if you use that model of a neutron actually having a proton attached to an electron, that's just kind of a model that's used in nuclear chemistry sometimes, but you would assume that small, almost massless electron does contribute a little bit of mass. And now we're going to do a fusion reaction. The last one we did a fission reaction. Here we're going to add a form of hydrogen, which we call deuterium, based on having 2 nucleons, and then you have a tritium, which is based on having 3. These two small particles collide in fusion, and they create a helium atom, basically throw off a neutron. So if you had the mass, the isotopic mass done by mass spectrometry, you could calculate the masses of the reactants and products, and figure out, according to equals mc squared, how much energy is associated with this reaction. And I'd like for you to calculate the energy associated with the fusion reaction shown above. Do it both in mega electron volts and kilojoules per mole. So again, this is a great opportunity for you to stop the video, do the calculation. When you're done, you can restart the video and check your work. So let's see how you did here. If you sum up all the mass of the reactants, you get about 5.03015 AMUs. If you sum up all the products, you get 5.01126 AMUs. And if you do your loss of mass, it's about 2/100ths of an AMU was lost in this reaction. And that's per atom of helium-4 that's formed. If you do your conversion, going back to that 931.5 mega electron volts per AMU, you end up with about 17.6 mega electron volts for every AMU of helium-4 that's formed in a fusion reaction. And then I asked you in this just to compare it, convert it back to kilojoules per mole, just so you'd have a relative reference point to the regular chemical equations we've learned throughout General Chemistry 2. There's 1.6 times 10 to the minus 16th kilojoules per mega electron volts. Finish out this conversion using Avogadro's number, again pulling in a little more significant figures than you may normally use. And your final answer is about 1.698 times 10 to the 9th kilojoules per mole of helium-4 formed. And again, we're on that order of magnitude of about 1 billion kilojoules per mole in these fission and fusion nuclear equations. Does it go with fission or does it undergo fusion? Just kind of in a qualitative sense, the way to think about what would make sense is that in order for the final product nuclide to hold together, the nucleus, all the parts of the nucleus have to be held within the strong nuclear force, and that's a very short distance acting force. We would assume that very small nucleides, if they combined, you could capture the parts within the small distance. So that's fusion. That's the model of fusion, where two small things combine to make a larger atom. On the other side of things, you can imagine that if you're at a very large nuclide, uranium-235, something like that, you basically are on the verge of already having parts in the nucleus that are about to, get out of the distance of strong nuclear force. So if you brought in a particle from the outside and it collided, you can imagine that that's disruptive enough to have a lot of particles, get out of the reach of strong nuclear force, and the thing will actually fission into two more stable isotopes. And again, the key word there is more. They're still not completely stable because they may continue to go through radioactive decay, as we've discussed in prior videos. So visually, the way to think about this is when you're on the top part of the periodic table, that's where fusion takes place. And when you're on the bottom part of the periodic table, that's where fission takes place. So that's kind of a visual of what's going to undergo fusion and what's going to undergo fission. So quantitatively, if you want to understand whether something undergoes fission or fusion, we do something called the binding energy calculation, and that will basically, it quantifies the strong nuclear force involved in holding something together. So here is what's called the binding energy curve. So it maps out the common isotopes involved in fission or in fusion, and it's interesting that it plots along a line here. And if you start on this end, as we talked about earlier, you basically are on the higher end of the periodic table. Along the bottom we have the actual mass number. So U-235 would be up in this area. So as we discussed earlier, that obviously is going to undergo fission. And then something small like tritium, deuterium that we discussed earlier, that undergoes fusion. And you'll notice on this chart, here's the deuterium down here, and here's the tritium. These two guys come together and they create the helium-4 product. Or if you had U-235 undergoing fission, as we described in the earlier reaction, you can see it decomposing into the krypton-84 and the other product that we were shown. They'll also be on the curve. But the way to read this curve is basically having more binding energy, right? Having more things grasped within the strong nuclear force. That would be the target, because the higher that is, the less likely it is to fall apart. And you'll notice that all of these things are converging on this maximum that's somewhere in the area iron 56. Just to have a stopping off point, somewhere in that neighborhood is where maximum binding energy is. And so anything below that would be more likely to undergo fusion. Anything above that would be more likely to undergo fission. And that's, as we discussed earlier, then fusion's at the top of the periodic table and fission's at the bottom of the periodic table. And reading this binding energy curve, that's what you would see. So the bottom of the table's on the right, the top of the table's on the left. The other interpretation I'd make out of this graph is just look at the slope on the fusion side of things. When you're starting with the smaller particles and your products are those combined, so you're working up this curve. Or if you're on this right-hand side of the table and you were undergoing fission, then you would be working down the curve into smaller particles. But look at the slope on this side. It's a lot steeper on the fusion side than it is on the fission side. And that is again indicative of the fact that fusion has about 4 times more energy than fission. But if you have this table in hand, this is how you can kind of know whether something's going to undergo fission or fusion and actually do the calculations. If you knew how to calculate the binding energy. So how do you calculate that? So you can think about this binding energy coming from the, based on this Hess's law type idea, is that if you knew the mass effect of making this isotope from its fundamental nucleons, its protons and neutrons, then you would know how much binding energy is present in the entire isotope, helium-4 at the end. So what you do is you just put together a very simple equation starting with fundamental nucleons, sum them up in order to make helium-4. You would basically take 2 protons, combine them with 2 neutrons, you'd have a helium-4 isotope. Go back to your isotopic mass table and these fundamental AMUs for a proton and a neutron. Go back to Einstein's equation, sum your products, sum your reactants. Again, you do your difference in mass. Your mass defect comes out to be about 0.03038 AMUs. Plug it into E equals mc squared. It's about 931.5 mega electron volts for every AMU. That ends up with a total of 28.29 mega electron volts. But if you divide it by the total number of nucleons, then you basically end up with 7.075 mega electron volts per nucleon. And remember, when we go back to that binding energy curve, that helium-4 shows up right here according to our calculations at about 7, slightly around above 7 mega electron volts per nucleon. And that's where these binding energy curves come from, just kind of using this Hess's law type idea to calculate the binding energy from the fundamental nucleons that make every isotope. So why don't you practice that? Again, what I'd like for you to do is figure out the binding energy in 10119. That was something that we had on our binding energy curve, so I'd like for you to do the calculation. Now again, remember that you will be given these isotopic masses. This isn't something you would know. You wouldn't know the isotopic mass of 10119, to all these. It looks like we got about 8 significant figures, but those are easy enough to look up, and you can find the isotopic mass. And then we always kind of stick with the standard isotopic mass of a proton and a neutron as was given earlier. So at this point, stop your video, see if you can calculate the binding energy for 10119, and when you're done, restart the video and check your work. So let's see how you did. Set up your fundamental equation, 50 protons, 69 neutrons, that's what it's going to take to get to 10119. Set up your table, figure out the mass of all the reactants. So usually these calculations are done in terms of mega electron volts per nucleon. So if you divide by the total of 119 nucleons, that's where you get back to this 8.5 mega electron volts per nucleon. And you can check back on that table, the binding energy curve, and you'll see how you came out on that and see that you fit right on the curve. So let's talk about fission, the chain reaction. Kind of now that we understand why you get all this energy because of a loss of mass, there's kind of an interesting effect that happens, because when we did the original fission equation of U-235, you saw that it split into 2 smaller isotopes, but you also released an additional 3 neutrons. So you could imagine if you had this large packet of uranium-235 present, and you brought in your original neutron and did a fission reaction creating the 2 new isotopes, you would also release 3 more neutrons. Well, if those 3 neutrons were released in this packet of uranium-235, that would continue to create more fission, and in this case it would triple, right? Because every time you come in with 1 neutron, you fission 1 material, you now have 3 neutrons that can fission 3 batches of uranium-235, and then that goes on and it multiplies up. So just for example, if that first fission, and you did your binding energy calculations, figured out is about 172 mega electron volts, then the next fission would undergo 3 times that, and then if you went another step, you'd be up to 9 times that. So in essence, you could kind of come up with this equation that said, look, if you get this much energy per every fission event of 172 mega electron volts, you take it times n, which would be how many neutrons come off. That would be 3, and you can raise it to the power of the number of steps that you're going to do. So in this case, it looks like we did 3 steps, so it would be 172 times 3 particles flying out raised to the power of 3 steps. So you can see that very quickly this energy starts to build up, and that's what we call the chain reaction. So that's where we get so much energy from fission. And now how do they harness this and use it? Because this fission reactions are something that we actually use to generate power in this around the world, and also maybe even in smaller power plants such as nuclear submarines, or we actually have some aircraft carriers out on the ocean. These are very large vessels that you can actually power off very little fissionable material because of the power of this chain reaction. But you could look at this and you say, well, man, how do you keep it from just turning into a nuclear bomb, which is kind of the precept of just letting, a chain reaction run unchecked. Well, we've learned over time that there's something called control rods. These are basically, cadmium, boron, hafnium. These are materials we know that absorbs neutrons. So if you build these rods out of these neutron absorbers, you can actually slide them in to the middle of the chain reaction and then selectively start absorbing out power of N, in essence. So instead of now releasing 3 neutrons, you can actually absorb out some and just kind of have a controlled chain reaction, and you can insert the rods more, or you can insert the rods less, and that's kind of the key to, and again, this is a very simplified diagram, but that's the key to how we've learned to harness the chain reaction. Some of the issues, though, with fission is that this looks great, we're generating lots of electricity, we have ways to control it, but some of the issues are, first off, the water that's circulating through this reaction to pick up all the energy, a lot of it times that water picks up the neutrons, and that makes a heavy, what we call heavy water. It's got a lot of extra neutrons, and that undergoes radioactive decay. And then also, if you go back to your prior videos and look at how to predict whether something would undergo radioactive decay, you would see that the byproducts of these fission reactions almost always create new isotopes that themselves are radioactive. So the problem with fission is that all the byproducts basically are radioactive. So we have to manage that radioactive decay so that we don't expose people to radioactive poisoning, in essence. So here's a diagram of a nuclear reaction, and you can just kind of see the general idea that if you were running this nuclear reaction with the control rods and generating all this heat with every fission reaction, and you were circulating water through there, then that water could then, this piping hot, high pressure water could be brought over to a steam generator. And of course, these are two separate, you might just go, well, why don't you go directly here? But again, I want to remind you that the water that's involved in all this nuclear, closest to the nuclear reaction, will now be radioactive, so that's why you isolate it. But anyway, you can basically then do one more transfer, generate all the steam, and you're right back where you are in a conventional coal-fired power plant, where you have extremely high pressure hot steam, runs through a steam turbine generator, rotating a magnet within a coil, creating electricity. But of course, associated with these nuclear power plants, and you'll see that in the picture, you have to be close to water, as you do with any kind of power plant, to cool down the reactor and keep the heat under control. So here's a similar idea where you basically take the same design, run it in a smaller type steam generator, and you can actually run a turboprop that's attached to a submarine or a ship. And the reason why that's where you might make this sort of application is because the presence of so much water, obviously, in an ocean-going vessel. For cooling purposes, you can run, nuclear-powered submarines or nuclear-powered aircraft carriers, and then on a very, very small amount of fuel, you can power these things for months at a time. So, talking about the applications of fusion now. This is the tokamak reactor. This is basically where you've contained this highly energetic type reaction. The problem with this is that you have such high startup energy that this hasn't really taken off. In order to get that first neutron impact, to get this reaction going, to generate all this actual heat, you basically have to start up at what they say is close to the energy of the sun. Now, we don't really have materials that can contain that kind of heat, so the tokamak reactor is a magnetic field. It's a very large magnetic field. You get these particles. You shoot those in there through a particle accelerator. The way you maintain the heat is you suspend the plasma ball, which is where the fusion's taking place. You suspend it in magnetic fields in a vacuum evacuated chamber, and that way there's no particles to transfer heat back out unless you harvest it selectively. And this is the idea. This is very much in the research phase, prototype phase. We're not really using fusion reactors to create energy. We have a couple issues. One is just the startup is so high energy content. The other issue is that we have lots of deuterium. So for this particular reaction, we found that deuterium and tritium is a very common reaction to use. It's kind of nice too, because basically the reaction creates these two particles, and that's what you can harvest the particles, or the impact of the particles being shot out from fusion, and that's where you can kind of harvest this heat. One of the issues though is tritium is not so abundant. The good parts of this is beyond the high energy that's created is the byproducts are not radioactive in this case. You basically have a helium particle and a neutron. Of the particles, these are the safer particles to create. The other good part about this, the other feed source is deuterium, and that is very abundant. So how are we getting there? And I've kind of got this website. You might want to refer to this. It talks about a joint project in Europe where they're really working on scaling up this fusion reactor and working out some of the details. And if you go to this www.iter.org, you can kind of read some more details. It's very interesting research. We're thinking that by 2035 they'll really have this thing up and running and have a large load of fusionable material in there, get to startup, and then once you have this fusion started, you want to have all the fuel in place so that it can run years at a time before you have to pull the whole thing down, restart it, get back up to temperature, and restart it again. Now, on this particular ITER prototype, they have a few little ideas that I do want to share with you, which are kind of interesting. First off, you have this particle accelerator, and that's what's needed to feed the tritium and deuterium into this, the plasma ball area, and that requires a particle accelerator. Well, one of the byproducts of doing it this way is you're already bringing the reactor up the starting energy that's required. So that's kind of one of the ways that you kind of kill two birds with one stone, so to speak. Now, the other thing that's kind of neat about this is you have this abundant source of lithium, and so what they've done is they've shrouded the blanket for the ITER reactor in lithium. And there's this little reaction of lithium interacting with the neutron, and it basically does a little alpha emitter, but it also creates some tritium. So this is really a nice side reaction by which we can in situ create the tritium that's missing as one of the fundamental fuels for making fusion a reality. Fusion's a great reaction, a lot less radioactive waste, 4 times the amount of energy created per gram of fusionable materials compared to fission reaction. Some of the problems are coming up to temperature and also this source of tritium. Well, with the ITER reaction, we've kind of bypassed both of those problems by the way we feed the reactor actually creates the heat. And then the other issue is tritium sources. Well, the byproduct neutron that comes out of the reaction shoots into the blankets around the reactor, and those actually create tritium, so we can harvest that in place. And that's what we have here, where you're showing the blanket and it's creating tritium, and that gets put back into the fuel source. So just in summary, when you start to compare fusion to fission, the technology's worked out. Fusion, the technology's in development. The problem with fission creates radioactive waste. Fusion, minimal radioactivity, and what radioactivity is there is actually harvested to create energy. It creates radioactive particles, but it doesn't really create radioactive isotopes in a waste sense. Obviously, the energy is less than fusion on this side, and keeping in mind that the energy in the fusion reaction is, I have 3, but it could be anywhere from 3 to 4 times what's created in fission. The problem with fission, You have a large startup energy as well, but it's actually sustained by the chain reaction. And we've already worked out this technology. It's used, like I said, in power plants and in ocean-going vessels and in potential space vehicles as well. And then the problem with fusion is this huge startup energy. Although we've learned how to confine that in magnetic fields in the tokamak reactors. So I hope that this video has helped you understand this third part of nuclear chemistry, which is really quite interesting. Compared fission and fusion reactions and compared those back to radioactivity, but more importantly to understand these reactions, to understand why something might undergo fission and fusion, to understand E equals mc squared and where this large amount of energy comes from, mass conversion. Familiarize yourself with the binding energy curve. Know some of these definitions. Know what a chain reaction is. Know how to use a nuclear reaction. And just be able to compare fission and fusion and compare and contrast and know the pros and cons, so as these technologies move forward, you can be part of the discussion. So I hope this video helps.